All right, everyone. So I'm Clint Hilliard, the programs director, and I was very honored to have Mr. Randall Iliff accept invitation to speak to us. Mr. Iliff has over 40 years of program management and systems engineering experience that covers developmental efforts ranging in size from just a few $1,000s to actual billions of dollars, and has built a solid record of disruptive innovation in the aerospace, medical, commercial, and consumer markets. Mr. Illiff works with Project Performance International as a course presenter and also a principal consultant, and is the founder of his own consulting company called Eclectic Intellect. Prior to his current positions, he was vice president at the award-winning product development firm BB7. He served there as a systems engineering manager for the IceCube, which was a university-led cubic kilometer scale neutrino telescope at the South Pole, and which we will be hearing more on tonight. He's been an engineering manager at the Motorola Government Electronics Group, a program manager / senior systems engineer at Martin Marietta Denver Aerospace, and a junior member of the Skunk Works Advanced Development Group at McDonnell Douglas Astronautics. Mr. Iliff has a bachelor's in engineering and industrial design from the Michigan State University, and a master's in systems management, research, and development from the University of Southern California. So with this end of this introduction, I'll now turn the virtual podium over to Mr. Iliff, and you can please take it from here.
Okay, thank you very much for the kind introduction. I'll go ahead and get the wonderful world of computers happy with me here.
If everybody else could be sure their mics and their video are off, that would be appreciated.
Okay, again, thanks for the intro. I've got to remember to dial back about 10,000 words of the stuff I send out for each of these, because all that really matters is somebody who's been doing system engineering for a long time, and at least this evening would like to share some of that experience with you from a rather unique application of system engineering. The presentation tonight is titled The Invisible Matters, and that's a little bit of play on the nature of the technology of the project, which is a neutrino detector, and you can't see those. But it also very much talks about the dependencies, the interactions, the logic, the origins of value that are present within a body of discipline like system engineering, that are you could even call them the first principles that give origin to all of the benefit in it. So this is an application of system engineering, not in the absolute detail you would expect in the SEBOC, but rather in the application of the logic used as a tool to facilitate development. So system engineering for the IceCube project was very much subordinate to the objective of designing and delivering it, rather than being something that was contractually required or a procedural deliverable as it might be in other environments. Basically, we got to decide how much made sense and to make a case for that and then do what made sense. But anyway, this is the story of how program management, an outstanding PM named Robert Paulos, or Bob Paulos, and I kind of conspired to put together a model for how you can design something pretty spectacular. But anyway, it's based on system engineering, and I hope you find it useful. It's important to note that the material in this presentation they're virtually all actual artifacts from the project itself. So nothing that you see here was created for the purpose of telling the story. These are the work artifacts that were used to actually conduct the project. And I'm very grateful to the National Science Foundation and taxpayers at large for having funded that work. And because of its public nature, we have the ability to share artifacts that would normally be hidden away in a vault someplace of some company. So that's kind of cool. But the important disclaimer is that any opinions, findings, conclusions, crazy ideas, or speaking in tongues that I do at any point this evening is just me babbling away, and it doesn't reflect in any way the views of the National Science Foundation, the University of Wisconsin, physicists in general, or even for that many engineers out there. So you're welcome to disclaim any part of the heresy that you feel need to. But anyway, so we'll start off with what's an IceCube. IceCube is a cubic kilometer, gigaton scale discovery class research instrument now operating at the South Pole. There's a bunch of superlatives in that. The instrumented body of ice at the South Pole is literally a cubic kilometer volume of region in which particles can be detected. That much ice happens to weigh a lot, which gives you the physical scale of it. There's a couple of visuals we've got coming up that will give you a sense of the size of it visually, but the thing is enormous, and you really don't get any sense for that just looking at drawings. You kind of have to see something like Sears Tower in Chicago and say, 3 times that tall straight down, huh? Anyway, it is hard to wrap your head around some of the very large project scales that were involved. It's a telescope, but it doesn't work in optical or radio wavelengths. It works in particle physics. And because of the way the array is set up, there is a block of sensors in ice, and any particle that transits that block of sensors through some of the magic of physics and muons and Cherenkov glow and a whole bunch of other things, generates a wake in light in deep ice that the sensors detect, put timestamps on, and are able to recreate through algorithms. Just like if you saw the wake of a boat, you could reverse it and say, okay, the boat must have come from over here. We can do that with particles that came from other galaxies. So that's a kind of a unique feature of the instrument. And as I mentioned, instead of light, this telescope captures ghostly, virtually undetectable subatomic particles. Those of you still wide awake at this time of night notice that capturing and virtually undetectable are kind of contraindications of each other. So the trick with these little guys is that they're magic if you can catch them, but how the heck do you detect something that has an almost negligible chance of having a collision with an atom, even if it's coming up through the core of the planet? So it's a pretty interesting trick. And it turns out, like, all of these things, there are solutions to them, but it creates an interesting problem space to operate in. So IceCube has now been operational for 10 years, and it's been producing some really great science. There's kind of a nice punchline at the end of this on all. So what's a neutrino? What are these things we're chasing? Well, they're the second most common particle in the universe after photons, so they're abundant. They're invisible, nearly massless subatomic particles. They travel at nearly the speed of light, or basically in whatever medium they travel at the speed of light. They travel in straight lines from their source. This is really important because the combination of factors here is building up to something pretty neat. They get there quickly, they travel in a straight line so they're not being distorted by magnetic fields or gravitational fields around them, and they're not absorbed by matter. So events that are creating these high energy particles that are so dense and so active that the light can't escape because of all of the stuff around them, or even the radio waves get absorbed before they make it out, the neutrinos are happily dancing out into space and carrying all of that information. So with a principle called multi-messenger astronomy, you're looking to add up information from multiple aspects of the physical universe. And if I can see something in light and in radio wavelengths and in X-ray and in neutrino particles or even other particles, then or spectroscopes, all kinds of things. When I add up that information, I have more than I can get with any instrument by itself. So that's the why that we're interested in neutrinos. So anyway, they make fantastic messengers because they come from some of the absolute highest energy events that humans have ever encountered in space, and well beyond our capacity to duplicate here on the planet at this point. So anyway, they make great messengers if you can detect them. Where do these guys come from? Really high energy events in space. Some of them there's lower classes of these things and higher classes that the physicist community I worked with spent a great deal of time educating me on, which I'm sorry to say didn't stick particularly well because I was more interested in making it happen than the physics of it. But the idea is that these particles come from lots of different places, and in some cases they arrive ahead of other information. So a supernova takes place, the incoming flux of neutrino particles gets here a little ahead of some of the other wave fronts, and as a result of that, it's information that can be used to alert a network that something has happened, and ground-based observatories should take a look. But anyway, so these particles come from lots of different places, including some kind of, you might even call them noise level interactions just in our own atmosphere. So the project itself is interested in the really exotic particles, the ones that are coming from extragalactic sources or have extraordinarily high energies. So there is a dynamic range aspect to the design of the instrument that says we're tuning it to catch particles in this energy range because we associate them with scientific interest. And an event in this instrument is simply the sum of which modules out of roughly 5,000 of them in ice saw a particle or saw light go by, and at what time did they see it. So the line in the middle of the screen is the light that's emitted in the opposite direction from the particle itself. And it has had a certain amount of energy deposited at these different sensors. The larger the ball of light you see, the more energy that it had. And then there's a time frame on this. So the earliest ones are in one corner, the latest ones are in the other. And it's complicated mathematically in terms of the number of calculations, but trivial conceptually to say if I have 5,000 of these sensors and some of them saw it and they saw it at these times, what's the best three-dimensional curve fit for a line going through that? And it turns out that the overall scientific requirement for the instrument is to be able to create a pointer like this back into the sky to the origin of any neutrino particle that the IceCube telescope detects, and to have an uncertainty range of basically less than the size of the moon in the sky. So that's actually a pretty good resolution. And to get that kind of angular resolution, you need a long base. The sensors have to be far enough apart that the line you draw on them, whatever error is present in that line, doesn't add up to an enormous angular error in the sky. So that's one of the things that drove the physical scale of the instrument. Another one is the energy level of the particles we are interested in and how rare they are. You need a relatively large volume of instrument over a relatively long period of time to collect the sample bucket that is statistically likely to have enough particles of high interest to feed certain science domain. So anyway, we had all of the classic convert from the scientific stakeholder context community into what does that mean in engineering terms so that the design of the instrument could take place. And we'll get into more of the system engineering of it. This kind of gives you just a sense of what the subject matter is. The things that do the work are these little optical modules. And what you're looking at is, think of it as beach ball size. I believe they're about 14 inches, depending on how you count the penetrator for the cable. But all of the eyes and intelligence, if you will, of the sensing side of this instrument are in these guys. And there's 5,000 of them, so they have to be manufacturable at a reasonable cost and pace. They have to be extraordinarily reliable because they're less accessible than spacecraft once they've been buried 2 miles deep in the ice. So for the instrument's 20-year life, we had to have inherent reliability in these modules that was on a class that you typically get only through MIL-S components on spacecraft design. We did it with commercial off-the-shelf parts. You typically have devices like these built in really tight clean room environments. We built them in manufacturing facilities at universities, and we used, in some cases, grad students to help us put them together. So the challenge was, how do you take a non-traditional environment and produce the same level of results that normally cost an order of magnitude or more complexity and expense along the way to do it? And it turns out you focus on the parts that are important. So on the left-hand side of the screen, these tiny little glass beach ball things were the majority of my thoughts, concern, and worry for a couple of years, even though the rest of the instrument has a lot of systems in it. If these didn't work, nothing else mattered. So on the right-hand side of this display, you've got a visual stack that stacks up the Empire State Building, the Jinmao, the Sears Tower. Whoever got the naming rights to Sears Tower, I'm sorry, because it'll be Sears Tower forever to me. But anyway, the Protonus and then Taipei. You stack all of those up on end. Imagine looking straight down into the ice and realizing that's how deep your sensors are in the ice. So the physical volume of ice, the bunch of little tiny dots you see at the bottom of it, is from about 1,400 meters down to about 2,450 or so, depending on how you count some of the instrumentation and cable weights and things like that. So you got to figure out how to get these things into ice and how to keep them working in there, and how to manage them as essentially remote devices. I mean, there's not much difference between how these things get new programming and what you would do with Percy on Mars. They have A, B, and C memories to them, and you never risk losing communication with one. So anyway, we built a bunch of alternate ways to try and get them back, as you might, but we borrowed from spacecraft patterns of engineering high reliability systems, because we found that we had a similar overlapping need. So IceCube to physicists, it's the world's most powerful neutrino telescope. It's got all kinds of potential for discovery, and if you're really lucky and your timing is good, it might even land you a Nobel Prize, which is awesome. And I very much wish Francis Halsen that distinction. I think it's a legitimate honor candidate for that honor. But anyway, for the engineering community, though, life is a little different. For us in the trenches, it's a massively complex story problem to solve, which is fun and fascinating and frustrating as all get out. It's a challenging environment that has little or no prior art. So if you're not comfortable with a blank sheet of paper and figuring it out, projects like this probably aren't going to be a lot of fun for you. But on the other hand, if you really like being on the crazy edge of inventing something completely unprecedented, there's no place like it. But anyhow, I liked it. But the key is, if it works, there's total anonymity. Oh, yeah, engineers designed it, PMs helped produce it, scientists are wonderful, awesome, salute science. And that's not a bad thing. It's their instrument, it's their job. But the key is, if it doesn't work, then there has to be somebody to blame. So engineers out there, enjoy the anonymity if it works, and try to avoid the blame, but it just seems to be that way everywhere. It's not any different at the South Pole, in case you were wondering. So there are two fundamental challenges for any project that has this kind of vision of what it wants to accomplish. The first one was the pure technical dimension. It's not easy to detect subatomic particles from other galaxies, and to do so with that kind of accuracy and timestamp and certainty in the entire scientific chain of data that's needed for publishing results. The South Pole isn't the friendliest place to do work, and it doesn't have particularly good FedEx delivery every afternoon. So you have to plan for an environment in which you don't have continuous access or the ability to do things. And we'll see the impact on that to both the programmatics and the design logic here in just a bit. And of course, as I mentioned, the need for extreme levels of reliability despite an extremely demanding operation and in a location that's not suited to, well, it has challenges, put it that way. The one nice thing about it is once you get these sensors down in ice, they're in a cold place that doesn't have any dynamics or temperature changes. So they will live as long as the design of the parts within them is set up to have them last. Anyway, they're very unlikely to be driven over, put it that way, a mile deep in the ice. The other part of this that was a challenge, and it's probably the more significant one from a pure intellectual standpoint, is figuring out how to take the logic and essence of system engineering and extract just the key elements of that system of development so that it could function in an academic setting. I had the advantage of extremely bright people, but I did not have any prior background in system thinking, the operation of large projects, the flow of development through any kind of gate process or through levels of review. None of that existed, so there were no precedents culturally to build on. There was a lot of really good tinkering capability, a lot of hands-on awareness of stuff, but not a lot of engineering. You mostly had physicists who had built things in the basement and taken them to the pole and tried them, which again was awesome, and they were wonderful colleagues, but I needed to find a way to bring in disciplined, repeatable engineering and consideration of factors that were essential for a 20-year reliable outcome that didn't need to be there for a let's take it to the pole and see if it works and we'll fix it on the fly if we have to kind of background. So I needed to elevate a lot of the cultural discipline that a group of people had found successful in the past to match an environment that they were not familiar with, but that myself and a few others had lived through. So we had to coach them up to the kind of game that they would need to play, and that meant keeping the playbook as simple as we possibly could. I would have loved to have done model-based system engineering. It was not within the reach of what we could do with the project. I would love to have had an actual database for requirements, doors or something from this decade. That was not an option. I can tell you that it is possible to do a $300 million hardcore development program using nothing but Microsoft Office tools, and at the same time not recommend that as something you really want to do if you've got better alternatives. But the reason that we did that wasn't that we were cheap or didn't have better options. It was that the culture of the community that needed to contribute would have rebelled against purpose-built tools for something that they had only partial buy-in to the conduct of. We had to operate in something that their common sense of, well, yeah, I guess it makes sense to figure out what it's going to see for environment so it doesn't get crushed. Probably a good idea. Probably makes sense to figure this out. From the standpoint of what we were doing, you couldn't push back on any of it because you could see it as all as useful or necessary or helpful to a project. But from the branding of system engineering and the appearance of complexity without benefit, we had to keep a lot of that stuff as low as absolutely possible. And probably below the level I would have really liked, but on the other hand, on time, on budget, and delivering in excess of technical performance ain't such a bad score. So the idea of working at the South Pole is a complexity on top of everything else. It drives the logistics. You have a balmy 3 or 4 months of summertime from basically around Halloween or so until the middle of February that you can land aircraft and get large numbers of people in and out of the pole. And then you're in winter over season where you're basically just trying to keep everything alive until that cycle starts again the next year. So all of the work that we did on the project, multi-year deployment and also a multi-year engineering development on it, had to be broken into chunks. And this single chart that you see, kind of fuzzy because it's just a visual from an artifact I had, but this is the secret ingredient, almost the Rosetta Stone of how it was possible to utilize the flow of time and the sequencing of program management activities to align with the lift that was taking place in the technical dimension. And without boring you about details of a project itself that's irrelevant, there were 3 blocks of design articles, and each of those was linked to the first season it would be deployed. So the initial articles that we created had never been tested in deep ice. We were able to simulate a large fraction of the conditions at pole, but there were areas of just uncovered risk. Those devices, because of the lead time to get them to the South Pole to deploy, to test, had to be frozen in their design and manufacturing before we had the ability to get regular verification information out of those articles through a system engineering lifecycle. So basically the timeline was such that we bet on the performance of those devices, built them, sent them en route to the pole, and then went into the lab and conducted more of the formal verification. We had kind of rock filter, send them, don't send them kind of level of confidence, of course. But we didn't have the full body of information about what we were shipping to the pole until it was already en route. So that meant that we wouldn't, and there's another overlap here, is that the information from deploying the first sensors would arrive back at about the time we had to freeze the second generation design. So there is a little bit of feedback from what happens with the first season sensors that makes it into year 2, but it's really the third season in this where all of the confirmation or redirection of anything that was necessary would make it into the design. So you have roughly 60 modules in the first year, you've got about 500, a little bit more in the second, and then you're starting to talk thousands of them after that. So we wanted to make sure we had converged on a really stable design. The other thing that's interesting on this is that the first sensors were meant to be operational instrument, not a test or throwaway string, so that even though they may have had some performance enhancements between block 1, 2, and 3, the instrument had to be able to integrate data from all of the sensors and meet its primary objective. So you could only get better, you couldn't approach a low point or creep up on acceptable performance. But anyway, this ability to know when this piece of information will appear in reality and when we will have hardcore verification in situ and thus validation of the overall design, the timing of those required us to stretch a development period over multiple years and to also integrate that in a way I've never had to do before into the system integration process. There's more overlap of the systems of validation, verification, system integration in this particular project than I'd ever had to deal with before. And it came from just the unique nature of logistics operations at South Pole Station. I mentioned we use a very simplified system engineering process, and I did a lot of things to make it as friendly and non-scary as possible. And even though we didn't in any way do waterfall and it was more agile than you could probably express in a simple chart, we communicated it as simply the lift of going from a concept to something in operation, and that we were raising the maturity in steps as we went along. And then we associated each of those steps with events and with the products that were artifacts of those events so that they wouldn't be hanging in space, so that people could say, oh, the reason we have a critical design review is because we're moving from one stage to the other, and this is the basis for us making choices on whether that's a good thing or a bad thing to do. So without turning anyone into system engineers or development project managers, we had to equip them with enough of the why we are doing certain things that they basically that they didn't fight the process, and even if they weren't advocates of it, they at least went along with it. So we had a whole bunch of people who really liked the idea and enjoyed it and came on board with the whole idea of closed loop design and system engineering. We had a lot of people who thought they were probably just fine without it. And we had a few people who thought that it was evil and meant to destroy their world and their empire. So we kind of ignored the latter group and worked with the middle group as much as we could and embraced the people who were supporters of it. But anyway, we presented it simply, we stayed with the logic, and we made it accessible and something that everybody participated in, not just a group of system engineers in a different building somewhere off on the side of the project. These just little bits of eye candy here. The chart that's on the left of this represents in the columns each of the major research institutions that were part of the original collaboration. All of the rows across that are the things that you need to achieve the types of science they were interested in. The chart over on the right is a conversion of those consolidated needs to well over 60 or 70 configuration items that together represent the physical architecture of the instrument. So other than the fact that it was done in Excel and Visio and a few things, there's really nothing magic about what happened here. Pure hardcore system, pure basic system engineering. Who are the stakeholders? What's the context? What are the external interfaces? What fraction of the total universe do I have to worry about? What's inside, what's outside boundary? Completely understood by all of the participants. And then whatever is necessary to the key stakeholders we brought inside. We argued and traded off in the cases where there were conflicting objectives, but for the most part it was everybody needs at least this level, and if I can hit X then everybody's happy. If I hit X minus 1 I can make 11 out of 14 people happy, things like that. So the simultaneous optimization of everyone's needs led to the architecture, and then that led to the allocation of requirements from each of these roles down into the individual CIs, which then for the most part were able to proceed as miniature projects. And like all system engineering, because we had confidence in how the pieces would fit in context at the next higher system, we had the luxury of being able to design at the lower levels with a much higher degree of independence and efficiency. We trusted the breakdown would then be reassembled on the other side. And we'd made use of the V diagram simply as a way of, for all of its faults, indicating to people that we break it down on one side logically and we put it back together on the other physically. And even though inside system engineering we can point to better models or weaknesses in all of these views, when you're communicating to someone who has never thought about the deliberate structured development of a system, what may seem very primitive to a practicing system engineer is exactly the bit of insight without overload that someone needs to be your partner on a project. We didn't want to turn people into system engineers. We wanted to turn them into successful partners in a development effort. And that's a very different threshold for you to work with. We didn't preach to them the terminology of system engineering. We helped them understand the intent by whatever we wanted to call it. So anyway, you do end up with a whole bunch of stuff to keep track of. I mean, that's an actual reduced version of the master tracking spreadsheet that I used to keep track of all of the pieces as they went through the entire time cycle of the project. And yeah, it's a big, ugly, honking thing when you print it out. But another part of the design to help us focus and the tailoring of approach for this unique environment was we wanted to concentrate on the things that are the most important. And again, the details are irrelevant other than you're seeing on the screen a set of optical modules on the left, and the gray box that you can just barely see that says event, that's the origin. That's the thing in physics that's outside the instrument and enters. And as soon as that has been captured in any way within our system, we don't want to lose it. So all of the devices that are between the gray event box and the storage over on the right-hand side are vulnerabilities, because any failure in any of those will cost us science data. And anyhow, that view, or basically tracing a thread of data as it moves its way into the system, provided a very high level of failure modes and effects analysis. Okay, what happens if we lose the in-ice and ice-top DOMS cables and connections? We're screwed. We don't get any science data out of it, and there's nothing we can do about it. Okay, well, that sounds like kind of an unpleasant outcome. How are we going to avoid that? And it says, put your attention here because these are the things that you can't tolerate very many of. Whereas information that simply was offline data processing, okay, we run the data tomorrow instead of today. It's an irritant. Nobody's lost anything. The world keeps spinning on greased grooves, and away you go. So it gave us a what do we care about and in what priority stack. And that was really important because there are never enough resources to give priority one attention to everything on a project. And calling everything priority one is just an abdication of the responsibility to put priorities in place. So we spent a lot of time designing an instrument based on what we thought good would look like. Because you only get one shot at drilling a hole 2,500 meters deep into the ice at the South Pole, and then you make another one, it's basically $1 million to launch a hole into the ice. So our intention was to not waste anything. So we wanted confidence in a system that could be partially verified through analysis, partially through a few other things, but not too much through analogy. There really aren't any other systems like this that you can say, well, their optical modules on the South Pole are like this and they work, so we should be okay. It's a complete blank slate. So we had to say, what are the elements of the system? What are all of the ways these are combined operationally? And then at what points do fractions of the complete instrument become available so that we can reveal another class of uncertainty and get information about it, and then add some more integration and reveal another uncertainty and get information about it. So the chart you have here is just a tiny corner of a much larger table that says here are all of the things in the columns, and then there are the verification objectives converted here to system test activity headings that say if I'm going to do this test, I need some of these, and some of these. It's in essence a shopping list from the view of design of what artifacts are needed in what time frame of the program management, production, and delivery to field. So this is what forced the refinement and creation of physical artifacts in a timely manner to happen. The testing wasn't driven based on when artifacts showed up. The testing was driven based on the need to get them to the pole by a date, and then hardware was driven into the testing so that that became possible. I've lived on projects that did it the other way. This was much more fun. When you model what happens from the flow of information, you get a picture that looks like this of the instrument itself. When you say, what kind of environment do I need to create a simulated South Pole with simulated neutrino events, you have to add a few things to a laboratory in Wisconsin. And what you see here in the blue are the things that were test infrastructure. And as you would expect, there are verification requirements in the design of some of the physical artifacts that will go to pole station that were there only for the reason of facilitating verification during the development process. But for the most part, we were trying to draw on the actual operational data hooks and transport paths because we wanted the highest confidence in the operational configuration of the instrument we could get. So everything that was used in the North America test lab, with the exception of the few things you see in blue, was an absolute one-to-one of the equipment you would see at the South Pole. And some of these things are rather large. There's 2,500 meters of cable that go from a surface junction box down to the deepest modules. There's another 800 meters of cable that runs from the most distant strings to where the central counting house is located. So you end up with some rather large physical things sitting around in a warehouse space for a while. But what you see on the screen here with the 5 big chest freezers, a couple of them are dialed down to -80 to simulate the surface tanks, and the rest are at -40 to simulate, this is C, to simulate the balmy temperatures that the modules will see in deep ice. But the tanks themselves are fully cold. The sensors are operating as neutrino detectors in a fully dark environment. And the cabling through the lids of these is light tight and for the most part RF tight, so that you end up with these things in a pretty good facsimile of what you would see at South Pole. And we were actually able to detect physical neutrinos in background radiation reliably with these, as well as the test signals that we were introducing. But to test timing, we wanted to be able to have absolute control. So we had a sub-nanosecond class timing source, and then very carefully figured distribution routes out to these things. But anyway, I spent a bunch of time in that area. This modified fishbone chart was sufficient to communicate to the entire project how all of the articles needed to come together and in what order to facilitate which aspects of testing, leading to confidence in shipping stuff to the pole for first season. And although the details on this are kind of reduced to the point where they don't much matter, you can see that bringing 3 big black lines in at the top plus one more thing gets you to a red bar. So I need one of these, one of these, one of these, and a little bit of magic sauce with a procedure. And when I've got that, I can execute a test. I add something else, I can get another layer of information. So you see here the essential, the flow diagram of how the logic of the instrument comes together, which is extremely useful for creating the flow diagram of task network of how the activities are to be sequenced and synchronized. And it was the simultaneous consideration of what path will development follow, what path will verification follow, and what project should, or what path should the project itself be following at any given time, that I think are major drivers of the reason this project was successful and so many others like it are not. Project management and system engineering were a synchronized, simultaneous domain, not something that was done separately, and certainly not something that was in tension with the other at any point. We went through the development tests. There are an amazing number of configurations you need to confirm all of the variables, even when you're using design of experiments to simplify the solution spaces. And it was just a question of set them up and run them down and do the tests. So we collected all of that. To get you to some of the kind of the eye candy of what this is all for, what you're seeing in this picture is one of the drilling sites, and the 2 tanks that are going to be subsurface here when they've had that pile of snow bulldozed back over them. These are the ice top tanks. There are 4 sensors that sit on the surface, and these sensors are they're physically identical, but they have been tuned in parameter space to focus on a different type of particle called an air shower particle. And it was a different research interest there. But because these tanks are a full kilometer in height away from the first sensor in the primary instrument, they're also used as part of a long baseline calibration leg. And they're further used in a veto capability to help the instrument strip out noise particles. We have a background rate of 1,000 hits per second and probably a few hundred events of interest a day. So getting rid of background any way you can is a big deal for total throughput on the instrument and the data transfer. But these surface installations could tell you if a particle was either going down into the ice from above or if it was coming up from below. And simply because of the types of particles we were interested in, if they'd made it through the metal core of the Earth, we knew they were of a class that had more potential interest to us than the ones that had just been triggered a few hundred feet or maybe a few miles above it in space. So anyway, we were able to use this as a noise veto and also as part of the calibration. But these sensors at the surface are in water tanks that produce extremely clear, purpose-built ice for the sensor, but it is surprisingly difficult to freeze ice at the South Pole. So one of the things that no one would ever believe is a story other than insiders is that we had to design a particular process and protocol and freeze control computer to manage the slow outgassing and freezing at the South Pole of these optical modules, because there's just enough heat coming from the electronics in the sensor to keep a liquid interface around them if you don't do that. So anyway, it takes about a month and a half to freeze a tank full of water at the South Pole if you're doing it and seeking optical clarity. So nothing is ever simple. The closer you get to any project, the more of those little cool things you'll find. But anyway, these are ice top tanks. Below that is a string of sensors that goes into deep ice, and this gives you a sense of the scale of what you have to do to get that string introduced into the ice. On the far top left of this, let's see if it'll show my pointer or not here, is a giant hose reel. There are hot water tanks here. There is a derrick that's used to lower these strings into the ice. But basically you have a 2,500 meter deep hole in the ice that you have melted with a basically 5 megawatt water heater and a big snorkel tube blasting hot water down. So you melt a liquid column roughly 1 meter in diameter, 2,500 meters deep. You pull the hose back out, and before that water has had a chance to freeze, you lower an electrical cable down, and at each roughly 17 meters or so on the bottom end of that cable, you're mounting sensors. And then the sensor cable extends all the way from the surface down to 2,500 meters deep. It's held in tension by some weights at the bottom. It is absolutely true vertical as a result of that. And once it freezes into ice, it is in a physical structure that is superior to anything humans could create on the surface of the planet. So it's an utterly brilliant idea to freeze 5,000 sensors into a single matrix of ice, but it requires that you create now an ice drilling capability, and the enhanced hot water drill became a spin-off as equipment that was necessary to fulfill the vision. We had a deployment need, and this was the support equipment that was able to do that. And all of this stuff has to make it to South Pole Station in the belly of an LC-130 that's on skis. The New York Air National Guard does an awesome job of supporting air operations at South Pole Station, but if it doesn't fit in a C-130, it ain't getting there. So the hot water drill had to be broken down into segments. Certain size shipping containers will fit. There aren't that many flights that you can get to the South Pole that aren't scheduled for stuff already. So just getting this designed into the South Pole to have the ability to deploy the instrument was an enormous parallel project, basically, that ran along with IceCube. But anyhow, this is capable of mounting the sensors onto the string. 60 sensors is mounted on the bottom kilometer of a 2,400 meter string. It's lowered into the ice, and then there's some physical connections up at the surface of it. And all of those 86 strings in the original instrument run sometimes as much as 800 meters in a surface cable run from wherever the string comes up to the top of the ice. They run horizontal over to this facility. And they come in opposite ends of the building, excuse me, because there's just too many of these things. So imagine something that has about the flexibility of a railroad rail, and you've got 80 of them to try and manage and horseshoe around at the South Pole. But anyway, the cables come in under the surface of the snow, they go up the towers at each end, and they cross over the big cable trays you see across the top of it, and they enter an RF, it's basically a Faraday cage room that has all of the computer gear in it to be able to pick up the very low level signals that are coming up even off digital signaling, and convert them to data that's then captured and can be transferred out of pole. Because snow accumulates at the South Pole, this building isn't just a building, it's a building on adjustable stilts. So not only the building, but the columns at each end and all of those 80 really stiff, heavy cables have to be able to be lifted in 3 separate increments to be a original construction lift 1 and lift 2 configuration. And that allows it to have the roughly 30 to 50 year design life at South Pole, because otherwise you add about a foot of snow a year and pretty soon you're under the snow. But anyway, lots and lots of levels of really interesting challenges to figure out. If there are any people who have been around radio, or particularly amateur radio or commercial communication sites, what you basically have here is the world's largest fan dipole. You have 40 cables on each side of this building that are hanging out in space, and that in some cases are 800 meters long, or excuse me, 800 meters on the surface and then another 2,500 meters down. So we have kilometers of cable out there, and their ability to pick up volts and amps of RF during certain conditions is quite high. So there are fairly robust bonding provisions. Ideally, you would enter with an EMI panel in one location for all of those cables. Simply wasn't possible because of the physical logistics of them. So we have 2 opposite side entry panels that are as bonded at an RF level as possible. There's still some RF voltage and current across them, but it's a fairly robust path. But had you not accounted for that in the design of the system, the differential voltage between one side and the other due to the phase angles of incident radiation from CMEs and all kinds of stuff would have made the instrument completely unstable. So layer after layer of detail on stuff. Final optical modules. This is all of the tension of that entire string of 2.5 kilometers is actually carried by cables that are pressing on these little glass beads that we have for sensors. So the amount of crushing force that these glass housings experience is extraordinary. These same housings that have to withstand better than 10,000 psi of overpressure, also because they're flown at one part of their transport life in commercial aircraft, you can't just seal them at room pressure. You have to evacuate them down to about half atmosphere and then seal the two halves, because otherwise they'll see a partial pressure differential and you'll lose the dry nitrogen environment and rot. Anyway, just another one of thousands of details of carefully ray tracing every step that happens on the logistics pipeline, every step that happens on deployment, every step that happens in operation, and essentially leaving nothing to chance. When you take a look at how the strings are laid out in ice, the triangular pattern is very deliberate because it makes nice stacks of well, it's an interesting shape. It's kind of a Liberty Bell shaped sensor volume that each one of the photomultiplier tubes offer. But this particular pattern is a very efficient way to instrument a body of ice and to provide the overlap, but also the imaging efficiency per dollar per sensor that we were after. And again, if you're looking at the scales of this, this is roughly 1 kilometer across on each of these axes. So you occupy a cubic, basically, that's 1 million kilometers, million square meters of surface area at the South Pole. So it's a very large physical installation at pole, but the part that's visible on the surface is very small. It's just the counting house location. But the other thing that's important about the design of this instrument is it's not just the 5,000 sensors that are part of the design. Every one of the optical paths between all of these sensors, and not just horizontal paths or vertical paths, but every combination of X, Y, and Z path that light can travel between these sensors is part of the instrument, because the ice that is physically part of that region has imaging properties that have to be characterized and defined and added into parameter spaces for the instrument to get the optimum yield out of it. It's also part of the physics of how you determine exactly where in three-dimensional space that module ended up, because a difference of a foot in your assessment of where it's at is starting to get into your sense of timing. With 5 nanoseconds of timing, very small physical differences started to add up into our RMS error budget pretty quickly. So anyway, corner to corner, worst case error from signaling, uncertainty in position, timing, processor, jitter, lag, you name it, all possible sources has to be under 5 nanoseconds for us to hit the imaging resolution, which is kind of challenging when you add it all up. The cool news about the project is that it did some really cool things. It was delivered on time, it was on budget, and that budget, if you count the contribution from European partners and in kind, is well over $300 million, about $250 million of that in direct cash from the National Science Foundation. But anyway, so a big chunk of money actually efficiently spent and executed and delivering discovery class results. And the sheer energy of some of these individual neutrino particles that this instrument detects are just mind-bogglingly large. One of my physicist colleagues, when we had detected the first big giga event, he calculated that the amount of energy a single particle had delivered to the instrument after traveling from another galaxy was roughly the equivalent of a speck of dust falling 3 feet off of your counter to the floor, which granted doesn't sound like a whole lot of horsepower and fun on a drag strip, but a particle that you could see with your eyes dropping 3 feet to the floor in gravitational space has an enormous amount of energy compared to a single subatomic anything. So you're talking trillions of times the energy that you would associate with normal particles that we encounter day to day. So anyway, things like that are just pretty amazing. There are things that I would hear when I would go to some of the physics conferences that still kind of boggle my imagination. There are researchers working with this instrument who are certain that what they detect with this will help them determine whether time travel is practical or not, whether there are wormholes in three-dimensional nearby space, all kinds of things. So the imagination of the researchers is truly stunning. And I am very grateful that they were able to translate all of that into, well, if you can give me this timestamp and this accuracy and this, then I'll have what I need. Because if I had to come up to speed on their physics, we would never have gotten anywhere. The cool thing about this is just doing something that has such amazing potential to help the world. There's a term here on the top of it called discovery class that the National Science Foundation reserves for some of its highest risk bets, if you want to think of it that way. Things that are major investments, but if they pay off, will have at least a 10-to-1 unlocking of some aspect of the physical universe that we've never been able to achieve before. And that 10 to 1, you'll be able to do things no one has ever thought of before, sounds absolutely wonderful at the beginning of a project until you're the system engineer going, okay, that's great. You're going to discover a bunch of stuff you've never thought of before, but as soon as you do, you're going to want the instrument to be good at picking that stuff up, and you're going to be mad at me because I didn't anticipate it in advance. So, not having a crystal ball or a time machine, what I was able to do along with a team of people was preserve every bit of instrument flexibility that it was possible to preserve. 5,000 sensors in ICE can be remapped to 5,000 individual sensors, one array of 5,000, 100 rows of 50. Basically, anything your human mind can conceive of can now be applied to partition the array because we gave them individual addresses. Wasn't that hard to do? Each module has an individual configuration table in it, so you're able to evolve them over time or to tune their parameter space with memory from original manufacturing and what was tuned in them to normalize them for common performance. You could shift or bias the entire array performance in terms of sensitivity or noise rejection or many other parameters simply because all of those were driven as variables that were trusted, programmed, and set, but which could be adjusted later on if new information came along. The only thing that we couldn't fix afterward was the raw reliability of communication and the instrument themselves, so that's where we poured all of our attention. And I'm very happy to say that we got very good people who were able to take talent and convert that into demonstrated performance, which looks a lot like luck, but people on the inside know the difference. There were at least a dozen things that we caught and trapped and stopped doing that could have been a problem if we hadn't been there, and thinking as system engineers instead of just thinking as more of a hobbyist kind of approach to doing work. Anyway, some parting thoughts on this, and then we'll have a little bit of time for questions. This was the largest single project in the history of the University of Wisconsin at the time that I was part of the project. There may be others since then, and 100 million becomes smaller and smaller every year, apparently, in hindsight. But anyway, the largest single project in their history, and the University of Wisconsin at the time was one of the top 5 research institutions in the US. So not only was this rather unprecedented for the university, it was a unique thing for the National Science Foundation to try outside of a very trusted group that they had worked with. So there was a lot of stakes riding on it politically and from the reputation of the university, and even state legislators who were involved in it because of, well, politics and the fact that they were trying to help do a good thing, but also because of it being good for them politically. But there were a lot of people involved in this. There was coordination with other universities, and just a fantastic community of really neat, down-to-earth human beings to work with. And part of the challenge of leaving a project like that or finishing up my stage of it was, oh, rats, it's over now. I mean, there were parts of it that were challenging and less fun than others, but it is kind of cool to solve a puzzle like that. But there is a point where you hand it off to other people and let them run with it, and then you go on and do other stuff. But there's always that little bit of, oh, rats, I wish there was at least some footnote somewhere that said, brought to you by engineers and project managers as opposed to just the physics community. But anyway, I guess that's part of the game. So kind of checking timing here. Go ahead and see how we're doing with the main group and what we have here for questions. I'll stop the share so we can get back in a visual with things.
Thank you, Randy. That was a really fascinating presentation. I am fortunate. Many years ago, I actually achieved a master's in physics, so I found this project particularly fascinating. I had a question to start off with. I know you focus primarily in the development of the system and stuff, but I was just wondering, has the envisioned reliability held up to the original visions and expectations, and what maybe were some of the biggest maintenance issues that have occurred since then?
The instrument has had no systemic reliability issues that I'm aware of. It's had a very small number of infant mortality that were accounted for in the design process, a very small amount, because we did test them for 60 days before we sent them down. So there was a burn-in period. We did everything we could to get rid of the front end of the bathtub curve. There have been no age-related failures that I'm aware of, and that I'm particularly proud of because we felt that aging over time was the dominant failure mechanism, that sooner or later you will have enough accumulation of oxidation on a surface, you'll grow a tin whisker, there'll be something somewhere. But we were able to manage the thickness of gold plating on physical contacts because a normal contact in aerospace is vibrating and it's wiping, and the gold migrates back to the surface of the connector, and it's self-healing in that sense. These are physically extremely stable, and there's no mechanism to offset the chemical migration of the nickel atoms and the gold, and eventually you get to a point where they don't work. You can buy time by having a higher thickness than you would use otherwise, but you can't really prevent that behavior. The biggie is oxygen, and the photomultiplier tubes require high voltage. So to me, the outliers, I've got 2400 volts, I've got ionizing radiation, I can create ozone in here. None of these are good for long-term reliability. So what are we going to do about that? And I had a colleague, George Anderson. There's two George Andersons who've been part of system engineering, and this is the other one, if that helps anybody. But George Anderson of Honeywell Aerospace and RCA and a bunch of others, he is an extraordinary mind for design and development. He's the true right stuff NASA kind of person, worked on Hubble and a whole bunch of things. Anyway, his knowledge of what works in space and what works on the ground guided a lot of the high-rel decision making. And for things like the high voltage power supply, we went through and altered the design of the vendor's basic model to eliminate any points. So you would have, basically no high voltage peaks. The charge differential was as smooth as you could get it. All rounded connectors, no points, no local field strength. We then did miniature trade studies. Everything was done by the book. It was just a skinny book, is one of the jokes I make. The trade study to determine the backfill that we needed for our reliability was about 3 pages long, and it was done in Excel. But it organized all of the variables that were important in our selection and put them in front of all of the people whose vision and decision-making power was necessary. So it functioned as the very best trade study I've ever been around, not because it was the fanciest, but because it put the right information in a useful structure in front of the decision makers very efficiently. So it was all you needed to choose between path A, B, or C. And we ended up with an extremely pure scientific grade nitrogen backfill on these where they were constructed. And that meant that other than the tiny amount of oxygen that outgasses from cables or wires or physical packaging, that we took as few nasty molecules with us. Then the other hazard is something that comes down a physical electrical cable or shock. So we had to make sure that they weren't damaged in transport. And I worried a lot about signaling and communication and picking up stray voltage ESD on these cables. Triboelectric charging is a big deal at South Pole because you have maybe 4 or 5% humidity. You're at effectively 13,000 foot elevation. There is no earth grounding to anything. The best you can hope for is bonding like you would in an aircraft. And people run around in rubber boots and fur-lined parkas. So I couldn't imagine a more graceful environment for ESD on the planet. Anyone who ever worked in a production ESD environment would be thinking, my God, you're describing hell on earth for a piece of electronics. And that was one of the things that I asked the physics community is, well, what do you do for ESD issues? Because I'd known about the reduced cooling that you get for electronics in thinner air and some of the more voltage breakdown issues. But we were asking them about what happens with ESD. So, well, we don't have any problems with ESD at the pole. Well, seriously, you don't? I mean, that seems kind of strange. So, well, yeah, we take a few duffel bags down of keyboards and mice every year because they go bad. But no, we haven't had any real ESD problems. My thought was, well, what do you think is killing those? Gremlins? And it turns out that you can draw a gigantic arc walking around on stuff. So we basically had to design stuff to be very tolerant. There were things that you would use around explosives or hazardous ordnance where you eliminate any charge differential before you make connections, and then you remove the grounding strap. So all of the protocols were there, but what wouldn't have been there was the recognition that something at the South Pole deserves to be treated like a satellite from reliability and like an ordnance depot from the standpoint of cable connections, and like a hazmat site from operations and physical work. People doing physical work at the South Pole are operating at high altitude, their circadian rhythm gets totally messed up, and you're lucky if they have a fraction of the common sense they would at sea level under normal conditions. The visibility for work is really harsh as well. So the surface junction box, the connections that have to be made between the cables and the ice and the ones that go to the laboratory, they had to be impossible to get wrong. They couldn't be read the connector, because how do you read something in blaring sunlight with nothing but snow around you in a metal box with sunglasses on that are dark enough to protect your eyes? You'd have had to light these things from the inside with lasers to be able to see them. So anyway, you had to do this by physical feel and location, and it had to be impossible to get it wrong, because if you got it wrong, you're out $1 million worth of string. So there were attention to detail aspects in procedures, in process, in the connections between devices that were big parts of the success of this. Everything interacted with everything else in some really large ways. There wasn't nearly as much independence between all of those 60, 70 CIs as might have made it real easy. But anyway, that's way too much for one answer, but it's a good shot at it.
Thank you. Yeah, does anybody else have questions? Please unmute yourselves and maybe turn on your camera. Yeah, feel free to just shout out a question.
No worries, thanks. So basically just
I have a question, Clint.
Sure.
That was really interesting, really excellent from the parts I did understand. When you opened up, you talked about the noise background was about 1,000 neutrinos per second, right, and the ones you were looking for were on the order of maybe 100 a day or something like that. I forgot the stats, but how do you know when it's the right neutrino?
Very, very good question, Mark. And that was a big part of a design aspect called local coincidence. Basically, the modules are smart enough to talk to each other. So a low energy event will only light up a small region. The particle has very little energy and it won't travel very far at a detectable level. So we don't really care about this. So if only one module sees a particle, it can ask its neighbors, hey, Clint, you see anything? Mark, you see anything? No, I didn't see anything. Oh, well, never mind. I'm just hallucinating. And it can clamp that one out. Or you can use what's called M of N. We could ask the 5 around us, and if 3 out of the 5 saw it, then we could class it as a probable piece of information to send up to the surface. But those thresholds were absolutely variable. Other than the transport pipeline limitation, we could unthrottle the thing to send up every little bit of radioactive decay from every stray strontium atom or whatever that happened to make it into any of the parts that went into it. We even had the glass that was used in these benthospheres, these deep sea instrumentation vessels, sourced from beaches that had less, I think it was potassium 40 in it, than the sand that was in other beaches they sourced from, because that lowered our background rate about 5 to 1. Because the largest background rate we had was just what was happening in the glass itself. When you get down below like the last 75 years or so of ice at the South Pole, there's no radiation in it. So it's only the stuff that's in the surface tanks that sees, human above ground nuclear testing background radiation. So the surface tanks have a little bit of background noise because of that we couldn't do anything about. But they're in such a noisy, low energy driven environment anyway that didn't really make much difference for them. So, but anyway.
That's interesting. And a second question, when you do look at the neutron streams that you're interested in, was there any philosophy or theory among the physicists that these were information bearing, in the sense that some physicists believe information is actually physical, so there's some way it's being communicated between source and receiver by some kinds of either energy or some particle?
Well, it's really interesting. When you're detecting the physical thing that left a high energy physics event in the core of another galaxy, it's not just looking at a picture or something or looking at the screen on my computer. This is the physical thing that transited across intergalactic space and arrived and whacked the nucleus of a water molecule at the South Pole. So that there is a purity to the chain of custody of information in something like that is profound. Now, the type of information that a neutrino carries is mostly energy level. There are different flavors of them. And apparently there are conversions between flavors of neutrinos that have a different class of information because the patterns of transition are another layer of insight. Kind of if you go back to the DNA molecule, that beautiful double helix that everybody sees in the labs, it's apparently far more complicated than that as people get more insight of it. That was just the most basic physical representation that gave people a sense of how much complexity was in the information. So there are combinations of particles in sequence. There are densities of particles. There are transitions between particle types. But mostly there's a coincidence between a type of particle and a type of radio emission and a type of light emission that when you stack those up give you a lot of insight as to what type of physical process could be doing that. And you can actually see layers of depth into physical processes as a result of what can't get out of the deeper layers in light or radio still gets out in neutrino particles.
Wow. So it truly is information streams.
Yeah, it is. And it's something you cannot get any other way. And it travels in an absolute straight line. So it's not bent or distorted. It's not lensed at all. And it's not absorbed. So it's only the sun that makes a kind of a shadow on the detector. The moon doesn't. The core of the Earth doesn't really make a detectable shadow. I mean, that's how penetrating these little guys are in terms of making it through matter. A 500 million miles of dust in space mean nothing to them, which is kind of cool. They're almost like you mix your particle things, but if you think of X-rays with humans and a doctor being able to see inside something, that's kind of the addition to the astronomy community they give. They let you look inside processes that are otherwise impossible to pick up. And then there are other wavelengths such as gamma and X-ray and things like that that can get combined with these. But neutrinos are special.
Wow.
Hey, can I ask folks to
turn
their videos on, and we'll get a screen capture for our records, if you wouldn't mind.
Yeah.
And continue if somebody's got a question.
Hey, they're all awake. That's amazing.
Yeah, they are awake. They weren't sleeping. Yeah. Okay, hold on. I'm going to do this here. Anybody else here? Screen capture. I'm also going to ask Dave. Actually, before I ask Dave to do the door prize raffle, I want to thank our speaker here. So I'm going to share my screen real quick and just I'll send you a copy of this, Randall, but it's just a certificate, you know, of our appreciation. We very much appreciated you spending time with us and telling us about the world's largest IceCube. I guess another question would be did you learn, what was the biggest thing you learned from this project that you then took, maybe like if there's one thing that you took on to future projects?
That's a really good question, and it makes a nice wrap up for this. Is it really cemented a sense that I have had since before the founding of Incose, that the power of system engineering is found in the logical connection of stages of development, and it is efficiency you get from things like MBSE or our million acronyms that people are expected to memorize and regurgitate, but they're not part of the power. And I was able to deliver everything that I would want from a formal system engineering engagement with maybe 5% of the formality that you would encounter in the average Incose meeting room. And as a result of that, I was able to draw on minds and participants that we normally exclude from the party. So I learned that, at least for me and my passion with system engineering, it is about taking the essence at a more accessible level to 100 times as many people as we have ever been able to reach, instead of becoming more and more attuned to the needs of the choir and working on our High Latin. To me, it's about getting it out and putting it to work and letting bright people with common sense embrace the logic and support it in their own way rather than maybe the narrow way that we've described. So anyway, that's what I got out of it. And it was the segue into then doing that for 250 projects a year at BB7, which was the next stage. So that's probably a good follow-up presentation if anybody's curious, is how do you put in place business practices that support everything from the development of state-of-the-art self-calibrating satellite instruments and things like IceCube to dental floss dispensers that are made in China for thousands of a cent. And to do that with the same workforce and the same processes and equal efficiency, whatever you turn them loose on. So that's a kind of a cool story for anybody who's in the maker hacker part of the world.
Thank you.
For another time.
Yeah, Dave, can you share the big wheel of luck, big wheel of Incose luck, and spin it?
I thought that was the biohazard thing on the bottom. No,
there we go. All right, so spin the wheel, and the Pador Prize was a book recommended by Randall. Let me see. It was called Integrating Program Management and Systems Engineering Methods, Tools, and Organizational Systems. So Brian Kunley, I'm going to use the email you registered with, and I will send you a copy of that book. Congratulations, Brian.
Thank you.
Still here.
And Brian, if you're curious about the reason for recommending the book, Incose and the Project Management Institute, PMI, along with the Massachusetts Institute of Technology, what was then the Center for Program Excellence, conspired to do research on what makes a successful development project and what are the characteristics in both system engineering and program management and the interaction between the two that are productive and healthy, and what are the characteristics that are a pretty good prediction that you're not going to enjoy the ride. So Dr. Eric Rebentish was the lead researcher on it. I had the honor of leading the Incose team that contributed to it. I influenced the architecture of the book and some of the mission of it, but I don't take any credit for the authorship or the content of it. But I can highly recommend it as, I think, the best document right now that discusses why system engineering and project management, program management need to be partnered up. And projects like IceCube were absolute testament. Nothing I talked about, Clinton, of success would have been possible with an adversarial PM relationship or somebody who only scored dates and money as opposed to what was being done at those dates and time. I had a partner in the development as opposed to a slave driver.
Very interesting. Thank you very much.
Yeah, that was one of the things that I get that sort of struck me when you were talking. It's like you sort of work to have those non-SC. You work to make the stakeholders not be turn them into SCs, but you were interested in making them successful partners in successfully building this thing.
I actually tried to infuse SE into every aspect of it, all the way from who brought the donuts to the conference room meetings.
Oh, really?
People are thinking about everyday things in system terms, then those habits become valuable in the moments when they're not realizing they're making design decisions, but everybody always is. So, and it was painless and it was fun, and you know, I get a little bit of occasional ribbing for it, but I got what I wanted and they liked it, and I figured no animals were harmed in the process, so the SPCA is happy and everything.
Okay, everyone, this sort of ends the presentation for tonight. So if folks want to stick around and chat, that's fine, but it's the end of this evening's event.
You've all been graciously listening to me. I'd like to thank you for your time and attention and participation in this. If we're not already connected on LinkedIn and that's something that sounds of interest, by all means reach out. I always enjoy adding new friends to this. And who knows, maybe at some point we'll be back and do another one of these, and maybe have a slightly larger audience and a little better lead time for promoting it. But hey, we've got it on the can. People can read it and watch it anytime they want to. Anyway, thanks again. Appreciate all of the support and making it easy for me on this end, Clinton. Take care. Good night, everybody.
Good night.
Thank you, Chesapeake.
You're welcome.